let me look at manipulations of some, let x and y be any two random variables, I do not care. Then if we define, say z equal to x plus y, what do I mean by adding? By adding I just mean, since x is after all going to be a number on as a result of an experiment, y is going to be another number, I can always add them. So if I do that, then z becomes another random variable. Defined for each point in the sample space, right? Remember, right, you do a composite experiment, whatever experiment, it spits out an x, it spits out a y. We are saying that then the z, the value of z is going to be the sum of those two values, x and y, so always. So z equal to x plus y means that for every realization, which is the correct word, of x and y, the realization of z is obtained by addition. So now we are interested, right, in the case that x and y are both discrete valued random variables, which is what we have been studying all these classes. So what can I say about the PMF of z? So I'll ask a question, distribution of z. By distribution I mean PMF now. For now. First of all, if x and y are discrete, it is clear that z also can take values only in a discrete set. So how do I define omega z? So omega z is basically obtained by saying all possible values of x plus y such that x y, right, I mean wherever x and wherever this xy point occurs in omega xy, in other words where the non-zero probability of the joint distribution occurs, then you add. So all possible such values will comprise the set omega z, and so if this is a discrete set, countable set, this also has to be countable. You cannot get something, this in some way cannot be bigger than this. Right. So this is countable when, that is omega z is countable when omega xy is countable. So how do I write out the PMF now? So if I want to take, let us say, just to introduce some variety, if I want to look at Pz of, let us say, w, instead of putting z, I am going, the problem with the letter z is that it is very difficult to distinguish between the lowercase and uppercase, right. So let us force a distinction and say, ask for put the argument as w and not as z, which is the whole reason for, right, introducing this notation, right. This is the name of the random variable, this is the value that it can take. There is no reason why this should be always some, look like this, or just conventionally people have been writing lower uppercase here and lowercase here, that is all. So what is this? How do I go about finding? It's not joint probability, no, it's, so it means this, right. You look at this diagram here, x and y, you look at this straight line x plus y equal to w, which is a deterministic straight line that you can draw, and you look at all the points that fall on that straight line that also fall in omega xy. So omega xy is as we said, is we have assumed that it is countable. So therefore there will be some collection of points here which will, so if this w is in, supposing this w is in omega z, that is, there is at least one point on that in omega xy which is on this straight line. Typically there is more than one. So So the probability that z will take the value w is the probability that xy can take either this or this or this. Just common sense, right? You build up your intuition that way. Remember, these are all exclusive events, and that if xy takes this value, it cannot, the pair cannot take this value, but the sum will take the same value. So we are looking at all possibilities which give you the same value for the sum. So therefore, this will be equal to, if you want to write it mathematically, you have to write it as P in terms of the joint PMF, Pxy x comma y. Here you will write x plus y equal to w, and with the understanding of course that xy are in, okay, we can put it here, comma xy in omega xy also. This whole thing is little somewhat longish subscript here, but or I don't know how else to say it, right? But you have to identify all these points. The situation becomes a little easier to visualize when you have only integer valued random variables. So now is a good time to define them. What is an integer valued random variable? Any random variable whose omega, the space is consists of a set of integers is called integer valued, right? So since the sum of two integers is always another integer, no matter what, right? So this is one of those terms which is self-explanatory. I don't think we need to write out an explanation for this, right? So then so this is of course our standard trinomial case, right? Not just that, in many, right, but that's the case, that the most interesting case that we looked at so far. Let me just make sure that there was an interesting property I did the sum of, okay, yeah, okay, we can also do that a little later, but let me see, just make sure that I put it in the right place so that I can talk about it here along with this. But first let us focus on the independent case, because why is the independent case easy to manipulate in such cases? This quantity has to be expanded first of all, so which implies that now I can write Pz of w has to be an integer, but before that we will write it like this, Pxy. In place of y I can put w minus x going from here, because y always has, if I say okay x is now the variable, right, of the summation just becomes x. I don't need to worry about y, because y automatically is going to be w minus x, or I could have written this w minus y comma y. Of course the understanding is that you only look at, right, those points in the summation such that this joint probability is non-zero. So this is the standard formula no matter what. Of course it conceals a lot of things like what are the limits on x and so on, right? So when you have integer value, that means x is going to be, small x is going to be an integer, w minus x is going to be an integer, w is going to be an integer. But I am writing is just to continue the notation, I am writing it like this. But in the independent case, supposing we will come to the trinomial example a little later. Look, if they are independent, right, what happens? First let us look at this, which is obviously, right, not trinomial, right, but I want to develop a very important identity here. I can write, now I can even dispense with the w, and I am going to put k and I and so on, right. So independent xy and integer valued, right. So independent and integer valued. not necessarily IID at all, but just integer valued. So Pz of k will be sigma. If I write this, what happens to this? This is a marginal, sorry, joint PMF which can be written as a product of marginal. So how will it be written? It is Px of something into Py of something. Now I put k here, so if I put I here, I have to put k minus I out here. Instead of that, in other words, I am writing I in place of x and k in place of w. Maybe, but that I wanted to do only after saying they were integer value, right? Before that, it's better to keep it as keep it as whatever, x, y, whatever. But once I say they're integer valued, I can write this, and the summation will be over values of I. Have you seen this kind of sum before? It becomes convolution, exactly. It's a discrete convolution of Px and Py. Note that the convolution is best written without any arguments. You do not write it as Pz of n equals Px of n convolved with Py of n, which is a nonsensical way, I believe, of writing it, right? We are actually convolving two sequences to give you a third sequence. What are the two sequences you are convolving? Px and Py. The PMF is a sequence and the output is another sequence, whereas we are using this Pz of k to specify that particular value only, not the whole sequence. If you coded this in MATLAB, for example, you would use only a statement of this kind. You would not use a statement Px of z equals, right? You try coding that in MATLAB, it's going to give you an error. You can't call convolution with right, Px of k. It has to be just input as just Px. I don't know how Python does it, but I am sure it's very similar. So this is a discrete convolution. So it's a very interesting result now, right? That is why it's preferable to do in this and a couple of other places. Right? We should typically go through the DSP course before coming here, right? Because in addition to making you mathematically more prepared, it gives you concepts such as these which are important here. So what we are saying is that the PMF of the sum of two independent random variables, provided they are integer valued, is the convolution. So they have, not only do they have to be independent, they also have to be integer valued. If they are not integer valued, then you don't get a nice straightforward convolution. For example, if x takes the values 0.25, 0.75 and 1.3 or something, and y takes some other 0.4, 0.6, you can't, right? Well, the values that z will take will not fall on any nice grid for this convolution to work out. And anyway, even a convolution over such a domain is also not so easily defined, I believe, right? It's only defined when the domain of Px and Py are the same, typically integer. So for this convolution to work, then therefore, right, you require both the independence first and foremost, and then we also require the integer valued nature, which is actually very commonly encountered in practice. So how do you apply this result straight away, right? What is the PMF of the sum of two diroles? You get a nice triangular distribution, do you not? From 2 to 12, which is the convolution of two rectangular discrete uniform PMFs. Sum of two binomials, this is a very important example which we have to look at. Now for this I am going to, let me just write it here, sum of two binomial RV, but not any two binomial RV, which we will do here. So I continue over here. So let X be, have the PMF binomial, let us say n1 comma p and y have the binomial PMF with n2 commas the same p. The p must be the same. In other words, we are looking at the number of successes in n1 trials being x and then n2 other trials being y, and x and y are independent. So obviously these trials have to be disjoint in some sense. There cannot be any overlap in those n1 and n2 trials. If they were, then x and y would not be independent. Then what can you say about z? Just by reasoning, without going into any mathematics. If you looked at n1 plus n2 trials together, right, that's what we are doing.
What is the argument about n1 and n2?
N1 is the number of trials that define x, and n2 is a different set of trials that define y.
Think about condition for them being independent.
These two trials have to be different sets of trials. There cannot be any overlap. Most important, right? I mean, when you say they're independent, I mean, I'm just telling you how this happens in practice, that's all. As far as the maths is concerned, you just simply write this. But to get the answer, it helps to visualize the situation. What we're talking about is what? N1 plus N2 trials now. So what is the answer going to be without any calculations? PMF of Z is going to be what?
Binomial of n1 plus n2.
Because P is the same. If P were not the same, then it's a painful, horrendously, which you cannot even do by hand. You have to feed it to a computer for different values of the P and Q or whatever, right? So for the same P, which means the same experiment is being repeated, the basic experiment, right? So this is going to be binomial with parameters n1 plus n2 comma P. Now the same thing, this result can be obtained using convolution, just to make sure. But let me not do it for the convolution for the binomial case. I will instead do it for a related PMF, which is a Poisson, where I don't have two parameters, I have only one parameter, right, for the distribution. So this is binomial. Keep this aside, or to prove this formally using convolution, I'm going to leave it to you to do that, because instead, as I said, we will do the convolution of Poisson. You have, let's say we take two Poisson random variables, again integer valued, but lambda 1 and lambda 2 can be any two positive real numbers, independent. Now again we look at z equal to x plus y. Here what do you think the answer should be in line with that? What is the sum of two independent Poissons? It's going to be another Poisson. How do we get this mathematically? This is what I will, just to make sure that you people haven't forgotten your convolution, we will do this the next 2-3 minutes. First of all, right, when I say Poisson lambda 1, that means omega x is the entire set of non-negative integers from 0 to infinity, right, and omega y is also the entire set of non-negative integers 0 to infinity. So the sum will be again the set of non-negative integers from 0 to infinity, right. So at least that part is easy to see. There is a notation for this, but I am not writing it. This set of non-negative integers, right, is has some z plus, some script z plus or something, but since we are already using z here, I don't want to use the, right, so that notation. So which implies that what? Now we have Px of I is going to be what? For the Poisson, please tell me what is Px of I? It is e to the power of minus lambda 1 power I divided by I factorial. Then py, now we want k minus I. So this is I equal to 0, 1, 2, so on. I am going to directly put k minus I here because I don't want it in any other form, right? I want just k minus I, isn't it? So this is going to be e power minus lambda 2 to the power of k minus I divided by k minus I factorial. Now k minus I is between but note that, okay, so between these two, what are the allowed values that you are going to look for I? I cannot go negative, it cannot go less than 0, it cannot exceed k either. So if you freeze k and say what is p, what is the probability that z takes the value 5 or 10? I can only go between 0 and 10 or 0 and 5. You can get the pairs 0, 10, 1, 9, 2, 8, but you cannot get 11 because you cannot add two non-negative numbers, one of them being 11, you cannot get 10. So therefore Pz of k is the sum. Again, this goes back to convolution, right? You've seen these kinds of things. This is the convolution of two causal sequences where you write sum from 0 to n. Remember, the limits don't stay as minus infinity to infinity, they become 0 to n, in this case 0 to I. So e power minus lambda 1 I by I factorial e power lambda 2. See now how you get the e power minus lambda 1 plus lambda 2, straight away you get that. Lambda 2 to the power k minus I by k minus I factorial. So now let me make sure that I can manipulate. I mean, I don't want to spend too much time manipulating this because actually it's fairly straightforward. All I have to do is pull out the it's actually extremely straightforward. E power minus lambda 1 plus lambda 2 will come out, right, and I multiply and divide by k factorial. So that what do I get if I divide by k factorial and multiply by k factorial and keep it inside? I will get I equal to 0 to k. I have k factorial in the numerator, I have I factorial, I have k minus I factorial, I have lambda power I and lambda 2 to the lambda 1 power I and lambda 2 to the power k minus I. So what is all of that going to become? It will just become, just want to make sure it's lambda, so k choose I, so there will be a k choose I term here. This lambda 2 to the power k also if I pull out, there's one more thing I can pull out, which is this lambda 2 to the power of k, yeah, I can pull out the lambda 2 to the power of k, isn't it? Yeah, I will pull out this lambda 2 to the power of k, but doesn't matter, I'll write it out here separately. We can always pull it out later, right? I'll write it here, and then this will be lambda 1 divided by, lambda 1 divided by lambda 2 to the power of I. Do I or do I not get this? I get it, right? Lambda 1 power I divided by lambda into lambda 2 power minus I is the same as putting it that way, and then this k factorial, if I put it here, that is an I factorial, k minus I factorial, just becomes k choose I. What is that summation? You pull out this lambda 2 power k outside. That summation is nothing but 1 plus lambda 1 by lambda 2 whole power k. What it? Huh?
I equals 0 to k.
Yes, this should be, sorry, I equals 0 to k. I wrote it correctly out there. Yeah. So 1 plus lambda 1 by lambda 2 whole power k. So if you manipulate all that, what do you get? So this whole thing becomes lambda 2 to the power of k multiplied by 1 plus lambda 1 divided by lambda 2 to the power of k. What is this equal? Exactly. So this becomes nothing but lambda 2 plus lambda 1 whole power k, which is exactly what we want. So actually I don't need to pull this outside, I can leave this as it is, right. In other words, I am saying let me add this 1 power k minus I for those of you that want to see the binomial expansion, but actually it is not needed, right. 1 plus x power n does not need the extra term. 1 plus x power n is what? 1 plus all those terms. So the 1 power k minus I is not needed, but if you want to write it, you can write it. So convolution works. The convolution of two Poissons is another Poisson, and this does not require the advantage of showing it for the Poisson is, right, I do not have to worry about an extra p. I just have only one parameter, which is lambda, or lambda 1, lambda 2. Whereas here this critically depends on writing the same p in both places. Of course mathematically you can do it, so I am going to urge you people to complete this derivation by yourselves, but it is actually obvious. I mean, if you look at the physics of the situation, there is no other way for it to happen, right. If it is the same p, then it is basically the same experiment repeated n1 plus n2 times, and the sum of x plus y can only be binomial with the increased n. There is nothing else that it can be. So there is actually so this Poisson is a very interesting case, right. You can think of a big Poisson. Now I can now break, I mean I can extend this to multiple summations, right. I can look at z equal to sigma I xi. I can do, instead of just looking at x plus y, I can consider, I can extend to z equal to sigma I equal to 1 to n, or if you do not like, okay, it does not matter, I use I here again, I equal to 1 to n xi, in the sense that I can do pairwise. Supposing xi's are IID Poisson with some lambda, what is that sum going to be? You can add it. Now remember, lambda 1, lambda 2 can be two totally different things. So if I add 2 Poissons with lambda and lambda, I get 2 lambda. So if I add it over n, I will get n lambda. So let me write it here. The n I equal to 1 to n be n IID Poisson lambda RB, right. Then z equal to the summation of all of them. These limits are important because if I take a smaller collection, I will not get n lambda. So this is going to be Poisson. This is one of the most interesting results in the theory, right, which says no matter how many Poissons you keep adding, as long as they are independent, the independent is built in here, IID itself, you get the sum of the parameters and lambda. For binomial, we have a similar result, and that's the last thing I want to say for today. A binomial can be regarded as the sum of n Bernoullis, or binomial n with parameter n. Why now? What is the, if I want to break this kind of summation down to the atomic form with each trial, I define x instead of xi, I will, okay, instead of starting with binomial, I will start with Bernoulli. That is, this is a basic head tail success failure experiment you are repeating n times, right. You have I equal to 1 to n. So what is now z? This will be binomial NP. This is no longer, obviously if you add 2 Bernoullis you are not going to stay within 0 1, you are going to become 0 1 2. But why do I get this result? As long as the P is the same in all. What is this summation exactly? It will be the number of the total number of times you get 1. I mean Bernoulli automatically is 0 1, right? I don't have to decide, it is no longer success failure, it is 0 1. When I say xi is Bernoulli, I am constraining xi to be either 0 or 1, nothing else, because they are random variables, they have to be numbers. So if I add a bunch of zeros and ones here, I will only add the ones, and that ones is the number of ones I get in the sequence of the n trials. The sum is automatically the number of ones I get. So addition of IID Bernoullis gives you automatically, it gives you binomial. So this is a connection between binomial and Bernoulli. For Poisson it stays as Poisson. Of course this is more intuitive to see, this is somewhat less intuitive to see, where what is the sequence of experiments that you have with NIID Poisson. That is a different issue, I do not want to get into that. I mean if you really want to think about it, you can think of, right, even this makes intuitive sense, right. If you keep augmenting a long sequence of observations, right, and the number of events in a particular time period being Poisson, right, if you keep looking at more and more observations for periods, then you are sort of looking at that situation, right, x1 plus x2 plus x3 over some 3 different time intervals, so that they are independent. X1 is the number of observations you make over one interval, x2 second. If the underlying process gives you this, right, is the same, governed by the same physics, then they will all be the xi's will have the same parameter lambda, and therefore x1 plus x2 plus x3 will be the equivalent of observing for such a long period of time. So that also makes sense. This is clear. I seem to be looking more in that direction. Let me also look this side, right, let's get some visual feedback. Are you happy with all this?